Hi, this video will cover the first two sections of Chapter 7 about exponential models and their properties and graphs. So I have a written introduction here, and I'm not going to go through the whole thing. But there are certain things that grow in a way where they grow by the same amount over and over and over again. If I were to, and the example here is if I were to give you $100 a week, then first you would have $100, then you would have $200, then you would have $300, etc. And it just grows by changing by the same amount over and over again. But there are a lot of things where when they change, they don't change by the same amount. They change by the same proportion or percentage. If you invest money, you would be paid interest not as a certain amount. The bank wouldn't say, oh, we'll give you $1,000. The bank will say something like, we'll give you 5% interest. The amount of interest is given as a proportion, and as the amount of money you have grows, the amount of interest also grows. It's not the same amount of interest every year. The amount of interest would be proportional to how much money you have. And so because there are so many phenomena that work that way, we want to have the mathematical tools for understanding them. And this is covered with what are called exponential functions. So our definition here is an exponential function is one of the form some number that's not 0 times some positive number raised to the x power, where that base is not 1. So the base b, it's positive but not equal to 1. And then a, that coefficient in front, can be anything except 0. So for example, I could have f of x equals 3 times 1.2 to the x power. I could have g of x equals negative 1/2 times 1/5 to the x power. I could have h of x equals 3.7 times 2.015 to the x power. These are all examples of exponential functions. Basically, you can file away the idea that is, if you have a function where the variable is in the exponent, that's what makes it exponential. And you do want to focus on that precise vocabulary because it's not any function that has exponents. It's a function where the variable is in the exponent. This here is an exponential function. 3 is being raised to the x power, the x is in the exponent. While y equals x to the third, we would call this a power function. The vocabulary is not fantastic because often we think of exponent and power as being synonyms. This very specific phrase, exponential function, is used for functions where the variable is in the exponent. So, assuming that our leading coefficient is a positive number, right? We're not going to worry about negatives. Exponential functions fall into two general categories. Exponential growth would be a function that starts off really slow and then grows bigger and bigger and bigger. It would have a graph something like this. An exponential decay would be where we start big and it gets smaller and smaller and smaller, closer and closer to 0. And you could experiment with this in terms of graphing a little bit, but it really just comes down to the base. Okay, so here is the rule. If the base b is greater than 1, then we have growth. And as an example, suppose we just had y equals, say, 3 to the x. If I make a little table here, 1, 2, 3, 4, 5, 3 to the first, 3 to the second, 3 to the third, 3 to the fourth, 3 to the fifth, it gets bigger, and it gets bigger quickly. This is an example of exponential growth. Sometimes people, when they're not being formal with mathematics, will still talk about something being exponential or growing exponentially if it's growing very quickly. And if the base is between 0 and 1, this is exponential decay. Suppose we had as our example y equals 1/2 to the x power. 1/2. 1/2 squared is 1/4. 1/2 to the third is 1/8. 1/2 to the fourth is 1/62. These are all small values and getting closer and closer to 0. So they're not dropping off towards negative infinity, they're just getting closer and closer to 0. If we were to graph these, we'd have a point here, and then a point even lower, and then a point even lower, and a point even lower than that. The whole graph would look like it's super duper close to the x-axis. That's what exponential decay looks like. Now, many real-world phenomena change in ways that can be described using exponential functions. Exponential functions are actually more useful for things that change over the course of time in the real natural world than other kinds of functions you've learned. So here's an example. Suppose a biologist observes a population of ants, and after t days of observation, the population is given by this formula. So A is the function that is counting the number of ants, and this is the formula that does it. We will notice that the variable here, which is called t, is in the exponent. So this is an exponential function. So what if we wanted to know the original number of ants? Original in mathematical settings is when time is 0, right? The very beginning of this process after 0 days. So we can say, all right, if t equals 0, we are plugging into this formula. Now, presumably you remember that anything raised to the 0 power is just 1. You can consider that a definition of what it means to take the 0th power. So we get 500. And that means we were starting with 500 ants. We have this population of ants, and presumably they will reproduce and grow and grow and grow. We started with 500 of them. How many would there be after 30 days? Well, now t equals 30. We have this function that directly tells us what the population will be at a given time. And this can be typed directly into the calculator. And if I round to the nearest whole number, which makes sense when we're counting animals, that would be 635 ants. So we've waited about a month, and there are 135 more of them. How about after 100 days? Again, we can just plug that in. The calculator will do all the work for us. We just need to understand how this function is structured. And this works out to approximately 1109. Now, after watching this population grow, right, we'll notice within 100 days it more than doubled. So presumably it's growing pretty fast. Biologists might be curious, when will the population get to 1 million? Right, they're growing faster and faster and faster. So at some point, if nothing interferes with this process, there will be 1 million of them. So let's just write an equation for that. So we want to know how long does it take. So basically, this is a when question. To answer a when question means to find t, to find the amount of time. So in this original expression, t is time, but this whole thing is the formula for the number of ants. So basically what we want is for a of t, which is counting the number of ants, to be equal to 1 million. And we have this formula for a of t. So this is the equation we would want to solve. Right now we don't know how to solve it, but we understand presumably there is some value of time that makes this equation true. In order to solve this, we need to think about how can we take this exponential function and apply it backwards. The calculator can do this for us, and you're going to learn how to do it very soon. The next part of this video is from the next section, which focuses on graphs of exponential functions. So if I go to Desmos, I think I have Desmos. Okay. Here's what we'll notice. If I have something like y equals b to the x power, and I add a slider here. Various values of b change the exact steepness of the graph, but we're noticing as I slide b back and forth, I'm getting more or less the same graph. When the base is bigger than 1, the graph falls into a very familiar pattern. And if the base is smaller than 1, it's also a familiar pattern. One was exponential growth, one was exponential decay, and those graphs are extremely similar. Exponential decay looks something like this version right now. If I make b bigger than 1, exponential growth looks something like that. So let's try to hammer down the general patterns here. If we have an exponential growth graph, and we're assuming we don't even have a coefficient on this, it's just purely y equals some base raised to the x power. The exact details will change depending upon what our base is. But the overall shape of the graph is something like so. The easiest points to plug in would be if x equals 0, we have y equals b raised to the 0 power, which is 1. So the point 0, 1 would always be on that graph. And if x is equal to 1, we have y equals b raised to the first power, which is just b. So we have 1 comma b. So this will change with the base, but if I tell you it's base 2, the point is at 1 comma 2. If I tell you it's base 5, the point is at 1 comma 5. And what's going on with this graph is that it's nearly horizontal on the left. And it grows quickly on the right. Nearly horizontal over here, and then grows really quickly. It's extremely steep. It's not vertical. It's not purely vertical, but it grows very steeply. This is when we have a base that is bigger than 1. So all exponential growth graphs have a very similar graph. And when the base is smaller than 1, but again, it has to be at least 0, the picture is essentially backwards. It follows the x-axis on the right, and it's declining steeply at the left. So it decreases steeply on the left and nearly horizontal on the right. The two easiest points are still the same. 0 comma 1 would always be there. And 1 comma b would always be there. Here we're assuming b is smaller than 1. So that's why this point at x equals 1 is actually lower. But it's still just plug in 0, plug in 1. So if you understand this, then any basic exponential graph, y equals 2 to the x, y equals 1/3 to the x, y equals 5 to the x, you have the gist of what that graph looks like. Just a bit of vocabulary before we start drawing more examples is what's called an asymptote. An asymptote is a line that's followed by the graph as a graph stretches out in some direction. And it might not be literally the same, but it's something that's super duper close. So what we're noticing is this graph here on the right. The orange graph is not literally the same as the x-axis, but the x-axis is essentially the line that is getting followed. My orange graph is just following along the x-axis really, really close. If you did this on Desmos and zoomed in, you would find just the tiniest of gaps between those two. And the same thing's happening on this one, just in the opposite direction. So for these exponential graphs, we will notice that the asymptote is the line y equals 0, also known as the x-axis. Now that we know this basic graph, all of our old rules for transformation still apply. So suppose I wanted to graph this function, y equals 3 times 2 to the x plus 1. What I will recommend is start with your two easiest points and just follow them around. So we're just going to do one example. So y equals 3 to the x is the basic function hiding in there. Y equals 3 to the x is this basic exponential growth function. We have a really easy point at 0, 1. We have a really easy point at 1, 3. Over here, we're following the x-axis, and then it's growing very steeply. Now we've made a couple of changes. We have a 3 in front of this thing. Oh, this should have been 2 to the x. I'm just going to cheat. Luckily, I don't have tick marks there. So we'll pretend that's good enough. Now we're going to multiply this by 3. Multiplying by 3 makes it 3 times as tall or steep. And what that literally means is each y coordinate is multiplied by 3. So let's just follow the easiest things. I'm now going to graph y equals 3 times 2 to the x. And remember your order of operations. 3 times 2 to the x is not 6 to the x. The power part comes first. There's basically implied parentheses there. It is 2 to the x, and then we're multiplying it by 3. So I had a point here at 0, 1. If I make that 3 times as tall, it goes up to 0, 3. I had a point here where y is equal to 2. If I make that 3 times as tall, it goes up to 1, 6. Over here, I have a bunch of points on the graph where y is really, really close to 0. I'm not labeling any particular points, but I notice there's this whole zone of the graph. In that zone of the graph, y is very close to 0. If I take some values where y is very close to 0 and make them 3 times as big, that's still close to 0, right? If I have a really tiny number and multiply it by 3, it's still pretty small. So our asymptote is still down there. So our graph has the same basic kind of shape, but it is steeper than it was in the first version. And now finally, this plus 1 at the end, that will shift the graph up 1 unit. So I'll squeeze this in over here. Y equals 3 times 2 to the x plus 1. So I had a point at 1, 7. When that gets shifted up, I had a point at 1, 6. When that gets shifted up, it goes to 1, 7. I had a point at 0, 3. When that gets shifted up, it goes to 0, 4. And now here's sort of the tricky part. We had this whole zone, again, where y is really close to 0. Even though I haven't labeled any of those points specifically, we need to think of this portion of the graph. It used to be really, really close to y equals 0, but a little bit above it. We're going to shift up that whole portion of the graph. So now it's not going to be close to the x-axis. Instead of being a little bit above the x-axis, it's actually a little bit above y equals 1. Often people will draw in a dotted line like that, if it's not one of the axes, so that we can see, oh, that's the line you're suggesting that this follows. And so we still have the same basic shape, but it is steeper than the original version and shifted up, including this whole portion out here. So you'll practice a little bit of this for homework. But it's the same transformation rules we've had since, I don't know, November, whenever we first saw this. Okay, that is it for this video.